Imagine you have exactly 20 minutes before your Cambridge IGCSE physics mock practical exam begins. Your heart is racing. You completely know the theory. You've studied the formulas, but every single time you face a practical paper, you bleed easy marks on data handling, missing units, and mixed up variables. Well, consider this explainer your high-stakes survival plan to stop losing those marks right now. We're going to tackle this through a step-by-step playbook. We'll start with how you plan your setup, then break down the variables and data types, and finally, we'll apply it all to a real Cambridge-style scenario so you know exactly what to do.
Section 1. Planning your physics experiment.
So planning an experiment often causes instant anxiety for students, and honestly, it's because it exposes a really fundamental gap in understanding. This is where ordinary textbook revision completely fails you. You literally can't just memorize your way through a practical investigation. You have to actually understand the mechanics of it. So, here is the single most important question you must ask yourself before touching any apparatus in the lab or before panicking and writing a single word on your exam paper. Ask yourself, what are we actually changing and what are we actually measuring? Seriously, if you don't know the answer to this, your entire experimental method will crumble before you even start.
Section 2. The 3 experimental variables.
Let's define the 3 main actors that completely control the outcome of any scientific investigation. Getting this right is your very first major quick win. You need to contrast these clearly in your mind. The independent variable is the one you, the experimenter, actively choose to change. You're in full control of it. You set the dial, so to speak. The dependent variable, on the other hand, is what is measured or observed as a result of that change. It strictly depends on what you just did. Let's look at a classic Cambridge scenario to make this concrete. Think about when you're testing a spring for Hooke's law. You decide the force, or the load, to apply. You are physically choosing to add a 1 Newton weight, then a 2 Newton weight. Because you choose those specific weights, the force is your independent variable. The resulting extension of the spring, how far it stretches before it snaps back and hits your finger, that's the dependent variable. That is the actual data you are measuring with your ruler to see the effect.
And to make sure your results actually mean something, we have the third actor, the control variable. This is any factor you must absolutely lock down and keep constant so it doesn't secretly affect your dependent variable and completely ruin a fair test. If you change the stiffness of the spring halfway through your Hooke's law experiment, or if the room temperature drastically changes and affects the metal, your data becomes completely invalid. The examiner wants to see that you know exactly what needs to stay the same.
Now, in a moment, I'll show you the examiner clue that changes the answer completely. But first, you need the framework that makes that clue obvious.
Section 3. Classifying your scientific data. Knowing your variables is really only half the battle. You also have to categorize the information you collect correctly because this dictates exactly how you design your tables and what type of graph the mark scheme expects you to draw. This taxonomy beautifully breaks down data into 3 specific types. First up is categorical data. This is data sorted into distinct groups that can't be ordered mathematically, like the names of different materials, copper, glass, plastic. Next, we have continuous data. Think of this like a sliding volume dial. It can take any numerical value within a certain range, like the temperature of a liquid cooling down or the exact length of a stretched spring. It could be 5.1 centimeters or 5.12 centimeters. Finally, discrete data. This is more like a light switch. It can only take certain specific values, usually whole numbers. For example, the number of protons in an atom. You can only ever have whole numbers. There's literally no such thing as half a proton.
All right, let's test this with a quick spot the logic challenge. Imagine you're doing a bouncing ball experiment. Could you estimate the dependent variable for a drop height of 2 meters if you already know the bounce height at 1 meter and at 3 meters? Take a second to think about it. Well, because drop height is continuous data that falls within a fluid numerical range, you absolutely can logically estimate that missing 2-meter value. It's gonna fall somewhere in between the other two. This is a crucial skill for spotting anomalies in your data tables during the exam. If your 2-meter bounce is somehow higher than your 3-meter bounce, you instantly know something went wrong.
Section 4. Let's look at a worked example using the critical angle.
We're going to escalate the stakes now and apply this exact framework to a top-band Cambridge scenario. Looking at this setup, it's fascinating how it translates pure theory into a real lab environment. We're looking at a ray of light emerging into the air from semicircular blocks. Your task in this exam question is to find the critical angle for different materials and describe the nature of the data you'll be collecting. So, let's break it down. Step 1. First, you actively choose the material of the semicircular block you're going to test. That makes the material your independent variable. And because materials are distinct groups, like swapping out a glass block for a Perspex one, this is categorical data. Step 2. You then use your ray box to find the exact value of the critical angle each time you swap the block. That makes the size of the critical angle your dependent variable. And since an angle can be 41 degrees or 41.5 degrees, it is continuous data. If you write this logic clearly in your exam paper, identifying exactly what you change and what you measure, you are securely locking in those method marks.
Section 5. Ensuring reliable physics data.
Even when students identify the right variables, they consistently lose marks due to poor data handling and just a generally weak exam strategy. This is exactly where the examiner's red pen comes out. You have to avoid these common pitfalls. These are brutal examiner penalties that will instantly drop you out of the top band. Things like missing your units in the table headings, never write the unit next to every single number in the table, just put it in the heading, or rounding your numbers too early in a multi-step calculation, which causes massive cascading accuracy errors. Then there's providing vague explanations for practical improvements, plotting the wrong variables on your graph axes. Remember, independent variable usually goes on the x-axis. And finally, making really bold conclusions that your data simply does not support.
This comparison brilliantly illustrates the difference between an average, stressed-out student's paper and a top-tier one. A flawed answer just states facts vaguely, forgets units entirely, and guesses a conclusion based on what they think should happen. But a top-band answer? It builds a strict, logical narrative. It states the core concept, it backs it up instantly with evidence and hard numerical data from the experiment, and then it finishes with precise scientific reasoning. You don't just tell the examiner what happened, you systematically prove it to them using the data framework we just built. Concept, evidence, reasoning. That's your golden formula.
So, the crucial point is captured perfectly in this quote straight from our source material. Identifying the independent and dependent variables allows you to know which factor is affecting the other one. That is the ultimate takeaway here. Clear identification reveals the true hidden relationship in your experiment. It is the absolute foundation of every single scientific method you will ever be tested on. If you understand the variables, you understand the experiment.
But here is the final provocative question I want to leave you with. Now that you have the experimental playbook and you've completely mastered data and variables, is your timed answer writing system actually ready for the final exam? You know the practical theory now, but how do you structure these perfect, top-band evaluation answers when you're stressed and fighting against a ticking clock? That unresolved problem is exactly what we need to fix right now. The next explainer completely breaks down the top-band evaluation framework so you know exactly what the mark scheme demands. Click the explainer on the left to unlock the timed answer writing framework you need to survive. And remember, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. Your mock survival plan continues next.